Section 2.2, we're going to talk about different sets, describing sets. The first thing I want to talk to you about is what in the world a set is. A set is simply a collection of objects. You can talk about a set in terms of actual physical objects, like the set of encyclopedias, the set of CDs, the set of songs on your iPad or on your iPod or on your phone or whatever it is you use. So you can talk about sets as actual objects like that. You can also talk about sets as groups of other things, like sets of numbers. Or you can talk about a set in terms of people, like set of people, like the people in my family could be created and be a set. So it doesn't actually have to be physical objects, it could be something else too. Elements are the individual objects in the set. So they are the encyclopedias that are on that shelf. They are the songs that are on your iTunes account. They are the people, individual people that are in your family. And then there's a couple of ways to describe sets. One is called the listing or the roster method. That's a really nice method when we don't have very many things to list out. Right? So if I wanted to list all the numbers from 1 to 10, fabulous, we just write a list. You want to list all the numbers from 1 to a million? Not so fabulous. Okay? The set builder notation is another way mathematically to provide for writing out how a set could look without having to list every single element. It has a little bit more notation involved, but the upside is that you don't have near as much writing involved if it was a long, for instance, a long list. All right, so some common notations used in set builder notation. Let me show you what it actually, some things that you might see when we're using set builder notation. The first thing is that you might see this symbol that looks like an E with the line through it. If you've had another class where you've dealt with sets, you might have seen this before. This means is an element of. So if we were describing certain kinds of people in our family, we could say, like if I talk about my family, I can say my daughter Abby. Abby is an element of Penn's family, right? I can do that. The same thing for your music on your iPod, right, or whatever, is that you can say this particular song is an element of the group of songs on my iPod, whatever I'm using. Another notations, these other notations are all different symbols for different kinds of number sets. So we've talked about some of these before, but we're going to talk about them specifically now. This is the symbol for the natural numbers. Natural numbers are also sometimes called the counting numbers. So think with me, when you very first learn to count, you start with the number 1 and you go up from there, right? 1, 2, 3, 4, and so on. Those are the counting numbers or the natural numbers. That is the natural numbers you first learn when you learn to count.
Is that supposed to be an N? Or is it supposed to have that one?
Yes, it's a double line on the left. It looks like an N with a double line on the left. When you see it in textbooks sometimes, it'll look like a bolded line on the left. That's a lot more tricky to sort of indicate when I'm writing my notation. So when people are actually writing it, they just use a double line on the left to indicate that. We're going to see a lot of double lines. It's a very good point, Nicole. We're going to see a lot of those in these notations, those double lines. So this is actually, and I'm going to use these notation symbols, okay? This is a curly brace, and I'm going to list out what we're talking about here. These are the numbers 1, 2, 3, and so on. All right, so what happens after, think about your cognitive development of what numbers are. At some point in first grade, probably, maybe even kindergarten these days, these numbers are not enough. You need one more number. What's the next number you add? 0. If somebody asks you something like, if I have 5 apples and then I eat all 5 apples, how many apples do I have left? And we need a number to represent that quantity, right? So we have that number 0. Once we include the number 0, we call these the whole numbers, and that's a W with a double line. Okay. So whole numbers are just like the natural numbers, except we add them, well, not add, but we include the number 0. Everything I'm doing beyond this is going to include everything above with one exception, and I'll tell you that exception when we get there, okay? So natural numbers are whole numbers. Do you know what numbers you include that in the next? Once you're thinking about your number development. Negatives get included next. Now, this is a Z. These are the integers. So we get the whole numbers, 0, 1, 2, 3, 4, and now we get their opposites, the negatives. So I'm going to put the dot, dot, dots here, and then I'm going to do -3, -2, -1, 0, 1, 2, 3. And additional numbers from what we had before. Integers, right? So somebody introduces this idea of borrowing money or something like that, and all of a sudden you have a negative amount because you owe somebody something. It's one of the ways that comes up. Or some parent just does something silly, right, with their kids. Like my husband did it. I didn't do this. My husband did it with my daughter when she was very young. She was learning addition, subtraction ideas, and he said, well, what's 5 minus 7? And the answer is, you can't take away 7 from 5. I mean, right? This is the basic concept first, because we don't have a way to express that. Once we have negative numbers, we have a way to express that. Any idea what comes after knowing positives and negatives? Decimals and fractions, and we actually group those all together. We call them rational numbers. Rational numbers is the Q. Let me go back to the letter Z. The reason Z is used is because integers in Latin has a letter Z or Z sound involved. That's why Z is used here. And then the Q here is involved because Q stands for quotient. Quotient means division. So we're thinking fractions here, but these are called rational numbers. So what we get when we get rational numbers is, I'm not going to write them out because I can't write a closed list, but we get all of our fractions that have either whole numbers or integers on the top and bottom, okay, or have a way to express them that way. It also means that they can be expressed as a terminating or a repeating decimal. So the things you don't get are what I'm about to include next. So all of these numbers above are actually rational numbers, because I could write each of those as a fraction. It's not a very exciting fraction, right? How do I write 3 as a fraction? 3 over 1. Not very exciting, but I could do it. So all of these numbers that I've listed so far are rational numbers. And then we have another one called irrational numbers. Your book uses, this is terrible notation because it looks like it's a 2. They use an I here. These are irrational. We're not going to see them used much, but I feel like you've got to know that they actually exist. Irrational are things like square root 2, pi, e. Those things that we can't sort of stop the decimal and they never actually start to repeat either. They have sort of this no pattern process going on. Okay. All of these numbers, however, so this is something different. Irrationals are not one of these above. That's something completely different. But all of these included are what we call the real numbers, and real numbers is the letter R. And you might be thinking to yourselves, well, isn't that all the numbers there are? I mean, they're called real numbers. The answer is actually that it's not. There's another number system that you may or may not have encountered at some point in high school called the complex or the imaginary number system. It includes square roots of negative numbers. It includes the letter I used as a number, that kind of stuff. We're not touching on that at all. But just I'm mentioning that this isn't all there is. There's other things beyond that. But this is the ones we're going to work with. In fact, we're not really going to see the irrationals used all that often, but the other ones we will. All right, you ready to take a look at some? Now we've got a little bit of notation to talk about. All right, we're going to talk about how to write the listing method versus the roster method. The listing method versus the set builder notation or set builder method for a couple of different descriptions. So the first one says the set of all natural numbers less than 5. Okay, so you've got to have that idea of what we just talked about, natural numbers. So if we're doing the listing method, this is a small set, so the listing method works really well. I need to list all of the natural numbers that are less than 5. So somebody tell me, what does my list look like? Okay. Does it include 5? Oops. Does it include 5? I'm sorry, I didn't hear. No, it doesn't. It doesn't because it used the phrase less than. Yeah, if it said less than or equal to, we would be able to use the 5. Does that make sense to everybody? So we're going to stop at 4. I like that. That's really friendly. I can write that in real quick and it's done, right? I'm going to show you the next method, not because it's particularly friendly here, but because it's friendly in other situations. That way I can actually create one example and show you what both of them would look like, okay? If you're using set builder notation, it always starts out with that same curly brace. So both of them have the curly braces. It also always has, we're going to use X. It wouldn't have to be X, but X is used frequently. And then it has a vertical bar. That doesn't look very vertical, but pretend. Yours will look much more straight, I'm sure. So X, vertical bar, okay? We read this as X such that. That bar is read as such that, okay? That's how we read that notation. And then we use the rest of what's going to come here to describe the x. So somebody tell me what's describing this set. Tell me one descriptor of that set. It's less than 5. What's there? Is it one more descriptor too? It's a natural number. There are 2 descriptors for our set. Do you guys see that? So I have this issue of it being a natural number, and I have this issue of it being less than 5. So we have to include a statement about each of those in some symbols next after this. I'm going to do the less than 5. It doesn't matter which one we do next, by the way. I'm going to do the less than 5 because that's usually what you'll see. So how do I write x as less than 5? You know that notation, right? X, the less than sign, the number 5. Now, this is not sufficient because -2 is also less than 5, but I'm not supposed to be considering it. 4.1 is less than 5, but this set shouldn't include 4.1 either. So do you see why this is not sufficient as it is? It's necessary. I need it there because I don't want to include like 6, but it's not enough. So the other piece, the natural number piece, looks like this. We do that same x as a descriptor. X is going to be having these following features. Do you remember that E symbol that looks sort of like a, it's called an epsilon actually, so it looks like an E going the other direction. It's an element symbol, and we need to say it's an element of the natural numbers. This is where that notation is going to come into play. This is highly unhelpful in this problem. I understand that, but it is not highly unhelpful on all problems. Okay? Is that good? We have another one? A different set. They're different options. Okay? Different idea, excuse me. All right, we can talk about sets being equal. There's actually 2 phrases. There's phrases of equivalent and there's phrases of equal, and they don't mean the same thing. I know in English we usually mean them to be the same thing. So you say something's equal or something's equivalent, we mean the same, that's the same word. In mathematics for sets, that's not the same phrase. Okay? Equal sets are sets that contain exactly the same elements. So if I talk about the set of people in my immediate family, and my husband talks about the set of people in his immediate family, we're talking about the exact same people. Are you guys with me? Okay. But if I talked about the set of people in my family, and my sister talked about the set of people in her immediate family, they would not be equal. However, if we include my daughter from Ethiopia in my family, right, there's 5 of us, right? I've introduced you visibly to them before, right? There's 5 of us. My sister has 5 people in her family as well. She has 3 children and her husband. Our families are not equal sets, but they are equivalent sets. Equivalent sets actually just means that they have the same number in each of them. Okay? So the set of numbers 1 to 5 and the set of people in my family are equivalent sets. That sounds weird. But that's how we describe them. That's the differentiation between the 2 here. Now, there's this middle definition here going on. This talks about a one-to-one correspondence. This is simply a pairing of elements between one set and the other one. Okay. So if we were using, for instance, the example of my set of my family members and my sister's immediate family members, we might do a pairing between the 2 husbands and a pairing between the 2 wives. We might do a pairing between oldest children and we go down the list, or maybe a boy-girl pairing or something like that. We might do something like this. But there's some way to pair them up so that each person has a friend. This is important when there's children around, isn't it? You've got this one-to-one pairing. A visual sort of to go with this is why there's a little space here, would be taking, for instance, the set of 3 letters ABC. We could take 3 of anything else. I'll do numbers 1, 2, 3, and making some sort of a connection between the 2 sides. Every letter has a number corresponding to it, and vice versa. That's called a one-to-one correspondence. The pairing that makes it work. And if you're able to do this pairing, then you actually have sets that are equivalent. It just means they have the same number. That's what that all means. All right, so let's take a look at this idea of equivalent sets then, or one-to-one correspondences to create equivalent sets. How many one-to-one correspondences are there within 6 elements of a set? So you have one set of 6 elements over here, and another set of 6 elements over here. The question is, how many different friendship pairings could you have? Okay, right? So you have 12 kids in your class, you have 6 girls, and you have 6 boys, and you want to pair them off for an activity. How many ways could you do that? Are you with me? So let's actually talk about it. I'm going to draw a picture. This picture is not especially helpful for the actual answer, but it's helpful to visualize where the answer is coming from. All right? So let's say that you had 6 people, and we'll number them 1 to 6. And you have the 6 letters. Okay? So we're going to go one person down the list, starting with person number 1 or element number 1. How many different ways or pairings could I make with person number 1 to the letters? How many different options could I pair that person with? There are 6 options, right? Once I do that and pick one, let's say it's the first one, I can't pair anybody else now with person A, right? Because that match has already been made. It's like if you're sort of doing some sort of an activity where you have the boys and the girls coming and they're pairing off to dance. If somebody's married, you've probably got one set that's not going to be broken apart and paired differently, right? Same thing. Once you make the connection, there's no more connections that can be made between one or two. How about the next one then? I've got now person number 2. How many different letters could person number 2 be paired with? 5. So there are 5 options for person number 2. So let's say person number 2 gets paired with person F. Person 3, how many options does person 3 have? 4. What's going to happen in general? Say that louder, everyone. Yeah, so we keep going down by the number 1. So I've got person number 3 has 4 options. Person number 4 has 3 options. Person number 5 has, and person number 6 has, I guess you could say no options, but they do have one option, I guess, right? Like they could still choose to not participate or something. And then what we do with the 6, 5, 4, 3, 2, 1 is we multiply. Okay? So we're going to multiply between these. We'll talk a little bit about why here in just a sec. Let's go ahead and get that value right now. We multiply 6 times 4 times 6 times 5 times 4 times 3 times 2 times 1. What do we get? 720. Now we're going to talk a little bit more. I can't remember if it's in this section or not. It's not in the next page notes, but at some point here in chapter 2, I believe it is, we're going to talk about what is going really on here. What's going on here is this way of counting things. And what we're doing is we're saying that if there's 5 ways that this activity can happen and there's 7 ways this activity can happen, then if we actually multiply the 5 times the 7, there's 35 ways that that can happen. This is just an example where we're actually doing it for 6 people. Okay? So there's this multiplication feature of ways. So there are 720 different combinations of pairings with simply 12 people involved. 6 in this group and 6 in that group. Is it any wonder it's hard to find the right person, right? 720 ways this could happen. It's crazy. All right, now I've actually referenced this description, but I haven't given it this name yet. Cardinal number is denoted as N of S. It's simply the number of elements in a set. Okay? So when we talk about the cardinal number set, we're just talking about how many things are in it. So if I talk about my family, what's the number of people in my family? 5. Okay? So if you talk about the number or the cardinal number of the encyclopedias on the shelf, you can count them up and they have a number that's associated with them. That's cardinal number. The notation for a set here is using S. The notation for the cardinal number of a set is N of S. That's actually a pretty convenient notation, right? Number of something. Finite sets are sets that actually have a number that we can associate with them, right? The number of people in my family, finite. The number of songs in your whatever, probably a lot, but probably finite. Right? It's finite. But there are things that are infinite. Infinite are sets that actually cannot have that ability, right? They don't have a fixed number associated with them. So you talk about, so one of the examples that I like to give in this is when we talk about in the Bible where God tells Abraham to go out and count the stars in the sky or the sand on the seashore. Think in infinite, right? At least we don't have a number that we can tack onto that because our view of the universe keeps expanding with our abilities and technology, right? We don't have a number to associate with it, so we would call that infinite. There's one other kind of set. This is an empty set. That's just a set that has nothing in it. So if I talk about the college students living in my home, it's an empty set because there are no college students living in my home. So we can talk about a set that contains no elements. It's just not a very exciting set to talk about, right? They're wonderful, those college students live in my home. They do everything fabulous. They don't exist, so we're not really talking about any people. But we talk about this this has a cardinality of 0, which just means there's nothing in that set. It has a notation. The notation for this, the cardinal number notation n, looks like this. So let me actually make mention of this because I always have students who use this. This is not the number 0. This is the empty set. So when you have a 0 with that slash through it, it can mean a couple of things in mathematics, but it never means 0. Some of you got in the habit in high school, maybe not you guys specifically, but I know other people do, of doing a slash through all their zeros. It's not good notation because it actually has a meaning that's not 0. It means either no solution in algebra sometimes, or it means this empty set, the set that contains nothing in set notation. All right, so what we're going to do next is we're going to actually find the cardinal number of each set. Okay, cardinal number again means what? Oh, we just did it, guys. What's cardinal number mean? Thank you, all read it at the same time. Got it. Number of elements in the set. So we're trying to figure out how many things we're talking about in each one of these descriptions. So I'm going to actually give them the names that they're next to. This is set A, set B, set C, and set D, so that I can use the notation n of A, n of B, and n of C, and n of D, okay? So as we're looking at this, we're trying to figure out how many items are we talking about. Now some of this looks a little bit like that Gauss stuff we did, doesn't it? Trying to figure out how many numbers are there. So you've seen this, you've been exposed to this idea before. How many numbers are there between 9 and 99? Are there 90? 91? How are you deciding, Taylor? What are you doing? Yeah, well, you were the one who said the 99, so yes, you, Taylor.
99 minus 8.
Okay. So how did you get 8, or where did the 8 come from? I see the 99. Why 8?
Because if you take 9, you're subtracting out the whole set, so it's 8, you're putting all the numbers.
Very good. So if we subtract, so this is the idea we talked about before, that if we have the numbers from 1 to 99, we have 99 numbers. But we do not have the first 8. The first 8 numbers from 1 through 8 are not included. So we subtract out 8. So how many items are in this set? 91. There are 91 numbers from 9 to 99. How about the second one? How many numbers are in this set? Or how would we find it?
You would subtract 2002 minus 1 and then divide it by 2.
Really close. Do we subtract 1? We actually subtract 0 because we would only subtract the previous number that would be included if we listed the numbers out. This actually is all of the evens from 1 to 2002, right? Which is all the even numbers. So if we considered all the even numbers from 1 to 2002, well, let's consider all the numbers. We consider all the numbers from 1 to 2002. We would have 2002, right? But we don't have all of the numbers. We only have half of them. So how many numbers would this actually be? 1001. C and D look so much harder than they really are. They look weird because you're not familiar with that notation, but let me let you think about with me how we read what's there. This says we want all the squares, we want x squared numbers, where x is 1, 3, 5, 7, all the way up to 99. So let's actually list what these elements were. Like if we were to list out these out in listing method, this would actually be the number 1 squared, 3 squared, 5 squared, 7 squared, all the way up to 99 squared. That's the description that this is giving me. Let me ask you a question. Does the squared have anything to do with how many numbers are in the set? does not. It's telling you what kind of numbers they are, but not how many of them there are, right? So this question is the same as asking how many numbers are there from 1 to 99 that are odd. How many are there? How many odd numbers are there from 1 to 99? There are 50. And again, we could think about what about the numbers from 1 to 100, right? 1 to 100 is the same question if they're all odd, because we don't really get the number 100 once we think we're only using odd ones. So this would have been like the one before. It feels awkward to write it, but it's really 100 divided by 2. There are 100 numbers from 1 to 100. How many of them are even? 100. How many of them are even? 50. How many of them are odd? 50. The other 50. All right, the last one. This says I want all x's such that x is equal to x plus 1. What number is equal to itself plus 1? So tell me what you're really thinking of phrase say. What are you really thinking of phrase say? Any ideas, Katrina? Yeah, this is a null set. There are no numbers that are themselves and one more than themselves, right? That doesn't even work. I mean, if you tried to do this with algebra and sort of tried to like solve this, what would happen? You'd end up with subtracting x on both sides. Like Shelby said, you'd end up with 0 equals 1. Really? Not in my number system and not in yours either. This doesn't happen. There's no number that is equal to itself plus 1 more. Right? So like Katrina said, this is actually the same as the null set. And how many items then are in it? How many items from the null set? 0.